So today we're going to be looking at the study guide for Chapter 9 Stats, which is all about hypothesis testing for two populations and situations. Again, most of the stuff is done in the calculator in terms of heavy lifting. The main goal in us is to interpret the numbers that we get. So let's start with the first one here. So it says a number of larvae in various fire and pinch ant colonies was gathered. Use a 0.5 significance level to test the claim that the variance in the number of the number of larvae in fire and pinch ant colonies are the same. So the first thing you need to focus on here is that they say we're testing a claim about a variance. So this is going to be an F test because we're claiming something about a variance, and variance is what we use to, F test is what we use to test claims about variances. So we have all our information here. What we're going to do is go to our calculator. We're going to go to, turn on first, we're going to go to Stat, Tests. Now if it's a variance test, we go all the way down to F, which is right there. For me, it's selection D. For some of you, it might be different. But we go to SAMP F test. We don't have a list of data, so we're going to go to Stats. And then we enter the data they give us. Now, the thing about the F test is that S1 should always be the bigger standard deviation of the two. So between 5.5 and 7.8, 7.8 is clearly bigger. So I'm going to do 7.8 as my deviation for the first, 40 as my number of total for the first, and then the next one is 5.5 and 50. So 5.5 and 50. Again, you do not use the mean or the X bar in the F test. It's just there as a distractor. You don't need it. Now, what I should have done before I entered all this in is write down my hypotheses. So let me go ahead and do that now. So I have HO and I have H1. HO is always that variance 1 is equal to variance 2, or deviation 1 equal to deviation 2, same thing. And then the alternative for a variance test is either going to be not equal to or greater than. So we're testing a claim that the variance in the colonies is the same. Well, if we're claiming that they're the same, that means the alternative is that they're not the same. So this is our claim that they are the same, and the alternative is that they're not. So when we do our little stuff here, we're going to make sure that this is highlighted there as being not equal to sigma 2, because that's what we're testing against. And then we calculate. It's going to pop up here. Give it a moment. There it goes. So we need the F and the P. So the F here is 2.011. So 2.011. Sorry, the calculator is just going to go in and out as I'm doing this here, but we'll make do. The p-value is 0.0209. So 0.020. We'll do 99 just to be accurate. So 9. So we got our hypotheses. We got our F, which is our test stat. We got our p-value. Now we need to do our comparison, which is our fail to reject and support stuff. So we have 0.02 compared to 0.05. Well, 0.02 is definitely less than 0.05, which means we're going to reject HO because the p-value is low. So we reject HO because it's a very rare chance of happening. So it's probably not HO, which in this case, since we rejected HO, that means we're going to support H1, which means that we're rejecting our claim. So we'd say that the data does not support our claim. So that would be the last step here, is to actually get the support, not support, and the reject or fail to reject statements. Again, all in all, most of this heavy lifting is done in the calculator, as I keep saying, but we do need to know how to kind of progress through the problem. So write down our hypotheses, get our F and our P, draw out a conclusion using reject, fail to reject, and support or not support. And again, the rule of thumb is if P is low, you reject HO. If P is high, then you fail to reject HO, because again, P is testing how likely is it for HO to be accurate. So if you have a very low P, it's a very low chance of HO to be accurate, therefore you reject it. If you have a very high P, you have a very high chance of it being accurate, therefore you fail to reject it. You don't support it, you don't accept it, you fail to reject HO. You support or don't support your claim, which is, again, depending on which one you're throwing your lot in with, essentially. So let's go ahead and go to the next one here. So we have two hospitals here. Looks like we have the average wait time for each and the deviation and the number of patients surveyed to get that. Now let's jump down here to what the claim is. So we're testing the claim that the average wait time for this hospital is less than the average wait time for that hospital. Okay, so let's write down our hypotheses first here. HO and H1. So average wait time. So if we're testing an average, that means we're going to be using mu because mu represents average. So the average wait time of the first is always equal to the average wait time of the second. That's how our null hypothesis works. And I should probably write down what my 1 and 2 represent here because I have two different hospitals going on. So I'll say 1 is equal to the last resort. We'll do that LR, last resort. And 2 is equal to what's a stethoscope. So that would be WS. So the claim is that what's a stethoscope's average wait time is less than that of last resort. So since I always really want mu1 first, so it'd be mu1 and mu2. If this is last resort and this is what's a stethoscope, and I'm saying that what's a stethoscope, this one here, is less than that of last resort, that means last resort should be bigger than that of what's a stethoscope. So that people should be waiting longer on average during last resort's hospital times than what the stethoscope's time, based on this survey here. And we're going to test to see how accurate that is. So this is what we're claiming, that last resort has a lower wait time than, or sorry, that last resort has a higher wait time than what the stethoscope. That's why, again, last resort's in front and being eaten by the bigger than sign. So if we're testing an average, we use one of two tests. We use either the t-test or the two-sample t-test. And so the question becomes, how do you know which is which? Well, if you're testing the difference between two average, then you'd use the t-test. Then you'd use the single t-test. If you're testing to see how two averages compare to each other, then you use the sample t-test, which is what we're doing here. We're testing the average of one hospital against the average of the other. So we're not combining them, we're not subtracting them, we're not trying to figure out their difference. We're simply testing to see how one stacks up with the other. So we're going to do a two-sample t-test because we want to keep our two samples there. And then we're going to enter our data, or in this case, our stats. So remember, the last resort we have is 1. So last resort has a average wait time of 12. It has a deviation of 2.5. Excuse me, sorry. Deviation of 2.5. And it has a total sample size of 400. And the same thing for the other one. So what's a stethoscope? The average wait time is 8 minutes. Again, got to be careful with the wordplay here. The average wait time after surveying 260 patients was 8 minutes. So the average wait time was 8 minutes. The deviation they say down here, right there, is 3.1. And 260 patients were surveyed. We make sure that this matches our alternative hypothesis. Our alternative hypothesis is that mu1 is bigger than mu2. So there's mu1, should be bigger than mu2. So we want the last one. Pool is always no. We go to calculate. Again, this last one here, the average wait time for what's a stethoscope, was said kind of weirdly because they gave you the patient number, the average wait time, and then the deviation in kind of backwards order. So just be careful to read the problem first before you blindly enter numbers in. All right, so again, we have a t-score here because it is using a t-stat, because it is a t-test. 17.44, so our t-score is equal to 17.44. And our p-value is 3.35 times 10 to the negative 53. This part right here is important. That e to the negative 53 means basically there's 52 zeros in front of the 3. So it's like 0.000000052 times 3. So this is a very small number. So p is equal to 3 points, let me write that down again, 357 times 10 to the negative 53. So this is a very, very, very small number because it's times 10 to the negative 53 bit there. So when I compare this to my alpha, 3.357 times 10 to the negative 53, that's going to be a lot smaller than 0.05. Because again, this number here is basically if you took this decimal and jumped it up 52 times, because you have to jump over the 3 for one of them, but if you jumped it up 52 times, that'd be what the number is, which is an extremely small number because it has a bunch of zeros in front of the number. So in this case, we're going to reject, quite strongly in fact, reject HO. And in this case, it's going to support our claim. So supports claim. Because it's such a rare event to happen by chance, that's probably happening because the wait time at what the stethoscope or is less than that of last resort, or vice versa. Last resort's wait time is much larger than stethoscope's wait time. So again, the key thing here about using a t-test was that we're testing two averages that were not being subtracted to each other. They were simply averages that we're comparing one to another. So if you don't hear the word difference, you're probably going to be using a two-sample t-test instead. In this case here, we got another one. So we have some data here. We have the number, the average, and the deviation. Okay, this is our claim here. So claim, and Mr. Paul's videos help students get to sleep faster. So they don't quite tell us an average or a percent or anything, not outright, but we can kind of infer this a little bit. How can we figure out if somebody gets to sleep faster? Well, that would mean that their average time to get to sleep was lower, right? Well, X bar here represents the average time to get to sleep. So this is probably another t-test one. And once again, probably another one where I'm not subtracting them. I'm simply comparing one group of people to another. I'm not trying to find their difference at all. I'm trying to find average sleep time on this one versus average sleep time on the other one. So this is basically going to be the exact same thing we just did, just in a little bit of a different format in terms of a word problem. So we still have average sleep time for the first group is equal to average sleep time for the second group. And then for H1, we have to figure out what kind of symbol is going to go between them. So I'll put 1 as the listening, so I'll put L, 1 is listening, and 2 as NL, not listening. So it says that the videos help students get to sleep faster. Well, if that's the case, that means the students listening to the video should have a lower average sleep time, or lower average time to get to sleep, than students not listening to the video. So that means that this, U1, should be lower than U2 because the average sleep time, the average time rather, to get to sleep in the first group listening to the videos should be much quicker than the group going second that's not listening to the videos. So same test as before. 2 Chapt, because we're not subtracting anything, we don't hear that word difference. We do have a list of stats here, so we're going to enter those in. And we're just going to go down the line. So X bar is 4.8, S is 0.85, N is 15. Go on, there we go. Then for the second round, X bar is 7.2, quite a bit high. S is 1.6, and N is 28. In this case, my alternative hypothesis is that the first set of data, which is listening to the videos, is less than the second set. So I want the middle one here to make basically a left tail test. Don't want pooled, go to calculate, wait for it to pop up. There it goes. So once again, we have our data that we can write down and interpret. So we have t-score, which is negative 6.42. So t-score, which is negative 6.42. And we have my p-value, or my p as the calculator says, which is 5.40 times 10 to the negative 8th. Again, another very small number. 5.40 times 10 to the negative 8. Basically, if you see that e there, that means you're probably going to reject, because this is going to be a very small number. Again, it's 5 with 7 zeros in front of it. So in this case, that number, 5.40 times 10 to the negative 8, is going to be much less than 0.05. So once more, let me actually type this out this time so it makes it a little bit more clear. Once more, we're going to reject HO, oops, capital HO. And that, in this case, we should have written down our claims. Let me do that actually. So the claim is that the videos help Mr. Paulus' students to get to sleep faster. So that's going to be this one down here. We're claiming that it helps them get to sleep faster so that their average sleep time is less than that of those not listening to the videos. So that means that if we reject HO, whoops, there we go. If we reject HO, that means that we are going to support claim, because that means that we have rejected HO, so we're going to go with the assumption or the suggestion of H1 as the more likely occurrence. So same problem as before, just the information was given to us a little bit differently. Again, no matter how the information is given to you, as long as you can identify where it's at, you can use it in your testing. I'll see this one here. So we're doing a survey. It says we surveyed 48 juniors and seniors. 35 of them believed something. 57 sophomore and freshmen. 36 said they believed it. Okay, so here's the claim here. So test the claim that the percent of juniors and seniors that believe their math teacher is a vampire is the same as the percent of sophomores and freshmen. So we're testing a claim about a percent. We heard that word twice, percent. So that's going to mean that we're going to do a 2-prop z test, because percents deal with z's. Z's how you get the test for percentage values. So before we do that, let's make sure to write down my hypotheses. So if we're doing percents, that means we're using p as a variable instead of mu. So p1 is equal to p2. And once again, it's always helpful to identify what 1 and 2 is. So 1 and 2n we'll say is juniors, seniors, and then 2 would be freshmen and sophomores. Puts SPH for sophomores. So how do we write our alternative? So we start with P1 and P2. And it says here that the claim is that the percent of juniors and seniors is the same. So if we're claiming that's the same, well, we can't write equal to again. We already have an equal to. So we write not equal to, because that's the opposite of what our claim is. And again, our claim is either going to be supported by HO or it's going to be rejected by H1 if that's the one that wins out. So whatever your HO is, your H1 should be the opposite. And again, it's either going to be bigger than, less than, or not equal to. In this case, it's going to be not equal to, because they didn't say more or less. They just said that the claim is that they're the same. So this requires a z-test. So we're going to go to stat, test, all the way down to the 2-prop z-test. Again, 2-prop being 2 proportion, 2 percentage, however you want to think about it to sink it in your brain there. Now remember, the x's here represent the number of successes or the number of yeses or the number of agreements, however you want to talk about that. But it's a number, not a decimal, or not a percent either. So this says 48 juniors and seniors, 35 of them believe that the teacher's a vampire. So 35 was our number of successes, quote unquote, and n was 48. That's how many people we surveyed. For sophomores and freshmen, it was 36 that said yes versus 57 that were interviewed, and making sure that our hypothesis is highlighted correctly, because if you don't highlight your hypothesis correctly, your test stat will be okay, but your p-value would be off, and that's going to affect how you draw your conclusion. So we click that, click calculate. Our z is 1.064, so z is 1.064, and our p is 0.287, so our p-value is 0.287. So if we start to compare this, 0.287 is much bigger than 0.05. So what we'd say here, since our p-value is high, that means HO is supported. So we'd say we fail to reject HO. Again, you don't really say you support HO, because you can't really support a null. You just say that there's not enough evidence to disprove it, which is why we say fail to reject. And then in this case, I should again put my C next to my claim. My claim was that they're the same. So it says claim that the percent of juniors and seniors is the same as sophomores and freshmen. So I'm claiming the null. So I failed to reject no. So that means that the null goes. I'm rejecting H1 instead. So if I fail to reject HO, and that's my claim, well, check mark means my claim is supported. So I would go here. Whoops, there we go. And I would say supports claim. I should say data supports claim, but I'm going to be a little bit lazy here just to make the video not too terribly long. So again, another case where the calculator does most of the heavy lifting. You just have to input the numbers correctly and interpret the answer they get you. in a correct fashion. Let's look at next one here. So this one's kind of the big one. So it says the number of cookies sold in the Claw Cafe on days during finals week and days during the week before. So we have final week cookie sale on top, and we have days before or week before finals week cookie sale on bottom. We want to construct a 95% confidence interval to estimate the average difference. So we're saying that if we took the average difference between um, or basically if we took both these tables and subtracted them and got the average of those subtractions, what would we assume that would be? Because again, this is just based on a sample, not the entire population. So what we're going to do is we're going to go to our calculator again, go to stat, test. Since we're doing a confidence interval, we want an interval. And since we're doing an interval about an average, we want the t interval. So the t interval is what you want to select here because it's the confidence interval for an average type of value. Now, in this case, we don't have any stats. We have the listed data, so we go over to data, and we'd enter our list as L1. Now, before I enter this in, I want to make sure I actually put it in my list, because otherwise L1 is not going to have anything in it. So let's go stat, edit. And so L1 here is our first list, so we'll call before finals L1 and during finals L2. So we're going to have 24, 20, 26, 18, 21. And then L2, we're going to have 32, 25, whoops, let me write that again, 32, 25, 19, 18, and 21. Can't get that 8 there. 18, there we go. Now, I said we were going to use L1, but I actually lied. We're not going to use L1 because we're testing the difference. So I don't want to use L1 or L2. I want to use the difference of those two lists. So I'm going to make a third one, L3. I'm going to go up to the top, hit enter. I'm going to type in L1 minus L2 because I want a list of their differences, which is what that table is. That table is a list of the difference of cookies sold between various days during the week before and the week during finals. So now that I have list 3 made by subtracting L1 and L2, I can go back to stat, test, and the confidence interval or the t interval. I can go into data and I can actually change L1 to be L3 because I want to use the list of the differences, not just the list of the first numbers I put in. Frequency is always 1. Confidence level in this case is 95, so we can keep it as 0.95 or change it to 95. It doesn't matter either way. We go to calculate, and we're going to pop up two numbers here in just a moment. The smaller number is our lower bound. The higher number is our upper bound. So our bounds here is negative 8.3 and 5.9. So negative 8.3 is less than the average difference, so mu d, which is less than 5.9. So a confidence interval is a little bit different than a hypothesis test in that you actually have a range of numbers, not a single number that you would reject or fail to reject or anything like that. But it's still mostly done in the calculator in terms of the heavy lifting, right? Now this one says, does there appear to be a difference in the average amount sold between finals week and the week during or the week before finals week? So is there a difference in the average amount of cookies sold between the week before finals and the week during finals? Well, here's how you interpret that. If your interval contains the number 0, so if your numbers from the lower to the upper bound go over 0, then you can assume that you're going to fail to reject. So here we can say based on the confidence interval, we can say because interval contains 0, we would fail to reject HO. Which means that in our case, we would assume that there is no difference. So we would assume there is no difference in the amount of cookies sold for the week before finals and the week during finals because our interval contains 0. So we're 95% confident, essentially, that 0 could be one of the averages that we have here. We just don't know because we don't have the full list of data. It's just a selection of dates, or in this case, days. The last one finally says to actually make a hypothesis test to test the claim. So let's go ahead and do that here. So the hypothesis test should back up our interval. So if our interval says that we're going to fail to reject, our hypothesis test should say that too. So let's go ahead and do our hypotheses. So HO and H1. We're dealing with average difference here. So we're going to say the average difference, which is mu d, is equal to not a variable, but a number, which in this case is 0, because we're saying that the difference on average between the cookies sold the week before and the week during finals is 0. Not is another number, but is 0 itself. And then our alternative, would be mu d, and it says that more cookies are sold during the week, during finals week on average than before. Excuse me. So we're going to create a hypothesis test to test this claim. And as I'm reading this here, that more cookies are sold during finals week on average than before, this is actually a little bit strictly worded here. So what I thought was going to happen actually isn't. So I thought we were going to conduct a difference test. But if you notice here, they kind of switched up on us here. They say test the claim that more cookies are sold during finals week on average than before, which means that we're actually not testing the difference. Testing the difference would be saying test the claim that the difference between the amount of cookies sold the week before finals and the week during finals is 0 or is not 0, something along those lines. This is actually testing the average of the week before compared to the average of the week during. So we're actually not going to do a mu d, we're just going to do mu1 and mu2 just like last time actually. So we're going to do mu1 is equal to mu2. Mu1 can be the week, what is our table? Mu1 can be the week before, mu2 can be the week during. So this would be the before week, this would be the during week. So mu1 and mu2. And so in this case here, our claim is that more cookies are sold during finals week. Well, here's during finals week, so that's the week when we think more cookies are sold during. And again, based on our confidence interval, we would fail to reject the fact that there is a difference. So we're going to fail to reject the fact that the difference between them is 0, which means we're going to assume that it probably is. So if everything works out, we should support our null hypothesis. We should fail to reject our null hypothesis here still. So let's see if that works out in our testing. So we have a t and a p-value. And let's go ahead and enter that data. Now, we already have our lists made. So when we go to stat, test, and we go to the 2SAMP t-test, instead of doing stats, we can just do lists because this list 1 should already contain all my numbers here, and this list 2 should already contain all my numbers here. So we can make the calculator, again, do the heavy lifting and try to figure out what the x's are and what the sigmas are and all that stuff itself. We can just give it the list of numbers. Let me just double check to make sure my lists are still in there. And they are, good. Again, I don't really need L3 right now because I'm not testing the difference anymore. So let's go back there. So I have all my before numbers entered in L1. I have all my during numbers entered in L2. My frequencies are always going to be 1 and 1. My alternative hypothesis is that the week before finals sells less cookies than the week during finals. Or as they say, the week during finals sells more cookies than the week before. So that would be a left tail test. And we're going to calculate. And we get a t-score of negative 0. Let me pop that back up here. 411, because that 6 is going to round that 0 up to 1. So 411. And a p-value of 0.347. So 0.347. Right, thought it was 7.4 there for a second. So our p-value, 347, is definitely greater than 0.05. So as we said before, we are indeed going to fail to reject. HO, which means that it's not going to support our claim because our claim was that more cookies are sold the week during finals than the week before, but we just failed to reject HO. So we're going to go with HO, reject the alternative. So that means the data does not support our claim, which again, we kind of knew was going to happen, thankfully enough, because our confidence interval kind of told us that. Our confidence interval contained 0, So we're going to assume that there's no difference between the 2 weeks, which means that this claim of there being more of an average the week during than the week before would be false, because we just said that there's probably not going to be a difference. Now, just as an aside, let's say I tricked this question up a little bit, um, and I did this. This is just kind of an addendum here. Let's say I say test the claim that there is a difference in average cookies sold. Whoops. Between the weeks. So if I said test the claim that there is a difference in average cookies sold between the weeks, that means, again, I'm back to testing a difference here, not just two averages. So that's when I would do the HO is equal to mu D equals 0, because I'm testing an average difference. And then H1 would be that mu D is not equal to 0, because the alternative of there being a difference is there not being a difference. It doesn't say either way, it just says whether it is or isn't. So our null hypothesis is that there is a difference. Our alternative hypothesis is that there's no difference. And what I would do there to get this value here is I would go to stats, tests, single t-test, because I'm testing a difference. So I no longer have two populations. I have one set of differences. And then I would use L3 in this list. So mu O would be 0, L3 would be your list, and then your alternative in this case would be not equal to, because you're claiming that there is a difference, which means that the alternative would be that there is no difference. And in this case here, we're going to calculate. Again, we're claiming that there is a difference, so I should probably put a C here. We're claiming that there is a difference, so I should put a C right there. Okay? Because if there is a difference, that means the difference is definitely not 0. The difference would be 1 or 2 or -5 or something like that. So we look at our calculator screen. T is negative 0.469. So T value is negative 0.469, and our P value is 0.663. So 0.6633, actually, if I do it a little bit more accurate there. And so once again, our p-value is definitely bigger than 0.05, so we would fail to reject in this case as well. So we'd fail to reject HO, which in this case would not support claim. And again, it sounds reasonable based on our interval, because our interval says that assume there is no difference, and we're claiming that there is a difference. We're claiming that there is a difference, which is counter to what our interval is suggesting to us. So it makes sense that we don't support our claim if we're claiming there is a difference in this case. So again, I kind of had to add an addition there just because the previous question didn't quite turn out the way I wanted to. So I wanted to make sure I do one where you're doing a hypothesis test on a difference of averages rather than just two separate averages together. And you can kind of see the uh, uh, differences between the two, not to be punny here. So between the two questions here, this one was telling you, okay, this average is more than that average, or this average is less than that average. Whereas this one is telling you simply there is a difference or there is no difference. So again, if you hear that word difference, you're going to use that single t-test, which is option 2. Whereas if you have two averages, before and after, or during or before, that sort of thing, then you're going to use the two-sample t-test. And then here, so last few questions here. The average weight of 20 backpacks in middle schoolers is 4.8 pounds. Deviation is that. 34 high schoolers backpacks is 2.5 pounds. A deviation of that. A hypothesis test is conducted for a claim. So the claim is that the average weight of middle schoolers backpacks are more than that of high schoolers backpacks. So is this independent or matched pairs? Well, again, matched pairs means that the data is like a before and after, that every part in the first situation is linked some way to every part in the second, which in this case is clearly not. The backpacks of middle schoolers have no link or connection to the backpack weight of high schoolers. So this would be an independent type of sample, because high schooler backpacks and middle schooler backpacks are completely independent from each other. There's no before and after or some sort of connection between them, as this backpack matches with this high schoolers or anything like that. It's just two separate populations, each doing their own thing, so it's an independent sample because the backpacks of one middle schooler has no impact on the backpacks of one high schooler. But because we are doing averages, so it says the average weight, and test the claim about the average weight, that means we're going to be using a t-test. In this case, a two-sample t-test because we have two independent pairs, one for middle schoolers and one for high schoolers. But we are simply going to be using a t-test because t-tests are for averages, remember z-tests are for percents, and f-tests are for variation or deviation. And lastly, just a reminder of how to figure out critical values. So your critical value for a 0.05 hypothesis t-test with 30 degrees of freedom. So this is where you go look in your table here. If it's for a right tail test, that means it's a one tail, right? Right tail is one tail on the right. Left tail is one tail on the left. And two tail is, well, two tails. Let's do the right tail one first. So the way you get your critical value is you take your alpha, and if it's a t-test, you look in the top section here. So basically when it says area in one table, think alphas in one tail, alphas in two tail. So my one tail alpha in this case, if I'm going to where my stuff is, there it is. My one tail alpha in this case is 0.05. Okay, so I go back here, 0.05. I have 30 degrees of freedom, it says. So 30 degrees of freedom is right there. If I said I had 30 samples or a 30 as an n, then I would subtract 1 from it. But it just outright tells me 30 is your degrees of freedom. So I don't subtract 1 from it here because it's giving me the degrees of freedom outright. So here's 30, here's 0.05. If we look up where they match up here, looks to be about right there at 1.697. So we go here and do 1.697 for a right tail test. For a left tail test, if you notice, there are no negative values in here. So for left tail test, all you do is you simply take the right tail test answer and just make it negative. So negative 1.697. That's all it is. And then for a two-tail test, what you do is you go to the two-tail column, find your alpha, find your degrees of freedom, and sync them up, which in this case ends up being about 2.042. So we go to our notepad here, and we go plus or minus 2.042. The reason we do plus or minus is because remember a two-tail is on the negative side and on the positive side. It's a very poor bell curve, I know, but that's why we have it as plus or minus, because one of these numbers, the negative version, is on the left tail, and one of them is the right tail of our test, essentially. So that's all there is for this study guide. Again, I know that it can be confusing knowing when to pick which test and kind of how to format your phrasing for your hypotheses and whatever. That just comes with practice, uh, thinking on it, reading it over. It will get better eventually. But again, if you have any questions, let me know. Otherwise, hope you enjoyed the video. I know it was a little bit long, a little bit dry. I am kind of tired when doing this here, so you have to apologize any breaks in my speech or stuff like that. But I hopefully helped you out. Um, enjoy the rest of your day. Have a good day.